So this problem on the singularity function, if you see, it's a more complicated example, and this is where you will truly appreciate the use of singularity functions. That you have a beam where you have different types of loading. You have a point load, you have uniformly distributed load, you have a point moment. I could have made it more complicated using a triangular load and other kinds of loadings and so on. But it asks you to find the deflection at this point D over here, which is from this A, it is at a distance of 1.2 plus 0.6, 1.8 meters over here, right? So we will see that how do we use singularity functions to solve this problem. Now, you see, one thing which you must realize, which is important here, is that in singularity functions for the uniformly distributed load, like or even the increasing load, you see the loads are open-ended. For example, it starts at A, but then it continues for the rest of the beam that is there. The problem which you are given over here, the uniformly distributed load, it starts at 0.6 meter and then it stops at after another 1.2 meters over here. So it is not an open-ended load. So this is an example where if you want to use the singularity functions or you want to use this table of the interrelationships, you have to first modify the beam and make this load open-ended. Now if I'm stretching this all the way up to here, at the bottom I have to apply an equal and opposite one pushing upwards to nullify that extra load that I'm adding. So let me make that modification of this beam and then come back and use the singularity functions to solve for the deflection. So now I have simplified the beam. I mean, not simplified, but put it into the mold of using the singularity functions, where I have taken this 1.5 kilonewton meter load starting from 0.6 to all the way to the end of the beam over here. And to nullify this additional effect, that is from here to here, I have applied an equal and opposite 1.5 kilonewton meter acting vertically up over here. Now, in this beam, of course, you need to find the reactions first to start using, because the singularity function expression for the moment that writes from the left and all the way to the right. So I went ahead and calculate the reaction for this beam. So this left hand reaction comes out as 2.6 kilonewton. The right one, I'm simply going to mark it and not even bother calculating, because in the expression that I'm going to write for the moment using singularity function, the rightmost tip load or the reaction is not going to come into place. So I'm just not going to bother about that one at all. So let me mark this reaction here as well. So here I have 2.6 kilonewton. Okay, so now that I have all the loads which are put into the mold for using this particular table over here, let me go ahead and write the expression for the moment. So the expression for the moment, if you start writing it out, it comes out as something like this. So the first one that is there, we have this 2.6 kilonewton acting vertically up, that is positive, and acting at this 0.0 over here. So first one is going to be 2.6. Why is it exponent raised to 1? Because for the point load, my moment becomes something like this. Okay, so next I have this vertically downwards 1.2 kilonewton load. So for that, the expression will be this acts at 0.6 meter raised to the exponent 1, and then I have my uniformly distributed load starting at 0.6 and continuing all the way to the end of the beam, pretty much like this one and open-ended. But one thing to note here, remember that the loading, this is a positive, entire positive diagram, so the loading it is positive vertically up, but this load is acting actually vertically down over here, so it will come out with a negative side. So let's write the expression for that. And the expression for that will have this one. So because I'm writing it for the moment, so it is going to be 1.5 divided by 2 x minus 0.6 square within the macular brackets. Last two things are remaining. I have another UDL over here, but this UDL, which is cancelling the extra UDL, is acting vertically up, so that will be written as positive, but that starts to act beyond this point, that is 1.2 plus 0.6 meter. Lastly, within the beam, I have this point moment which is applied within the beam, and this point moment is applied at this point E over here, which is a value of 1.44, and then so this is going to be directly this expression over here for the point moment, which is acting at x minus a. So in this case, the a is going to be 0.6 plus 1.2 plus 0.8, so it is going to be 2.6 meters. And also note one more thing, this moment is anti-clockwise. Here the positive convention is the moment is clockwise, so it is come out with a negative sign. So if once you keep a small track of these things, it becomes extremely easy while you're using this table to write the expression for the moment. So now you see the advantage that you have now. We took the original beam with this complicated type of loading, and using the singularity function I was able to write one single expression for the entire beam. I did not have to bother about, if you were doing using the second order method, you would have to take a section here, here, so 4 or 5 sections you will end up with, and then you have to use the continuity of the slope and the deflection. But unlike that, using this method, with just one shot I wrote the expression for the moment for the entire beam. So now you know that your m of x is nothing but equals to ei d square y by dx square, and all we have to do is to integrate this twice to get the expression for the slope. So I have this written out already, and I will go ahead and write out the final expression that you get. So after integrating 2 times, this is the expression that we get over here, and we have this is the expression that we get, and we have also introduced 2 constants of integration, c1 and c2. We can calculate from the boundary conditions that at x equals to 0, y equals to 0, at x equals to L, that is at 3.6 meters, your y is also equals to 0. So now you know how to substitute these ones over here and to get the constants c1 and c2. So let's go ahead and calculate the constants. So what you will get after you use the boundary conditions. So these are the value of the constants that you will get. You might substitute it and calculate and come back and check whether you get the same expression or not. So now you see you have the equation of the elastic curve nicely written out in terms of the x and the distances, and c1 is minus 2.692 and c2 equals to 0, and the problem asks you to find the deflection at the point D. Now you see the point D over here, it is at 1.2 plus 0.6, so that is at 1.8 meters. So now if you substitute here 1.8 in this expression over here, you see this one will stay because 1.8 is greater than 0. This one will also stay, this one will also stay, and beyond that all of these guys are going to be 0 except this one. So you will see c1 times 1.8, but this expression within the Macaulay function is going to disappear to 0. This expression will also be disappear to 0 over here. So once you go ahead and substitute that at x equals to 1.8 meters, so that is at the point D, you will get the value of the deflection as So you see, you get in this problem, you get this deflection after literally just a few steps beyond writing this expression for the moment. Again, I would like to remind you, if you were using the second order method, you would have to have 4 or 5 sections within the beam. You have to use and then depending upon the number of sections, twice the number of that will be your constants of integration. You have to use the end conditions and also the continuity conditions to do all that algebraic manipulation to eventually get the constants, put in the equation, to get the equation for the elastic curve, and eventually you will get to this, whereas using singularity functions you just got it within just a few minutes after you could write one single expression for the entire beam. So what I encourage you to do, that when you get problems, when you're trying to solve problems, try to use these singularity functions more and more to just make your life easy and cut short the computation time for these problems.